Okay, good morning to everyone. So, I'm not sure if this is working. Yeah, no. Yeah, now it's working. Okay, so hello everyone. We are here to introduce you to some of the research stuff that we are doing here. Well, this is going to be the first part of the visit, and then we are going to go to see our computing lab, where we do most of the stuff that we are going to show you, and the 3D printing lab is going to be quick. So I'm going to make a quick presentation, and later one of my colleagues is going to give you another talk. So basically what we are doing here, we have 3 research lines in this group. I mean, in all the school we have, there are different lines and main subject, and one of the core is divided into fluid mechanics and continuum mechanics, and we're in the part of continuum mechanics. So I'm going to show you some of the most cutting-edge stuff that we are doing. Mostly focus on structures and metamaterials. So because you are from a numerical background, so we are going to show you some numerical examples and some numerical formulations. As I said, for structures and for bioengineering, always structures with different materials and different behaviors. And there is another research line, which is machine learning, that my colleague is going to present you later. So, just a quick overview. Topological optimization are these kind of shapes that you see. So at the end, it's like optimize the structure. It's a structure that will remove the parts that are not working just to make it more light and more efficient. And there are different ways to do it. So what we have done here is to create a new way to do it. Why? Because the state of the art is that we only can do this with certain restrictions, with some fitting parameters, and also only applying boundary conditions of displacement. So, of forces. So we are working on a methodology that allows us to impose different boundary conditions, forces and displacement, without fitting parameters, and that allow us to implement different behaviors, like optimize for fractures, for heat transfer, whatever. And if you look at nature, obviously you have roughly the same results, but in nature there is no, a plant is not fitting parameters to see how it's growing. So this should be something in the background governing this. So we are going to rethink the methodology, and we are going to develop a model governed by the strengths and the energy that we have. So just to go quick, this is like a full pipeline that we are doing, and we are starting from the topological optimization, is that we impose some conditions and we create the structure. So instead of having the structure and calculate it for validation, we, through the calculation, we create the structure. So we do this the other way around. Then we have the metamaterials, which are the rebars that we have to create a shape. With the metamaterial, we need to create some fits, and then we can 3D print. This is a 3D printer that we are going to show now. You're going to see now. This is like 0.1 millimeters, so this is very small, and those small rivers are the metamaterial that we have. So, just for a quick introduction, what we are doing here is to say, okay, we know the boundary condition, we know the energetic behavior that we want to have, we are going to grow the structure. Instead of designing, we are going to grow the structure. And some application maybe bone remodeling or some specific pieces that we're going to see. And this is basically done that we have the energy, and the energy is our objective function. We are going to optimize this energy, and we are going to do this just changing the mechanical properties. So instead of inserting penalization, we are going to tune the mechanical properties to have the different behaviors. If you see here, in the pictures that you have here, this part is less stiff, and this part is stiffer. And the same happens in the bone. This part is very stiff, and this part is comfortable. So there are different scales. At the macro scales, you have that this core should be less stiff than this edge. And in the macro scale, you will have this pattern that reproduces what you have calculated. So this pattern is going to be the metamaterial, and the stiffness field is going to be the topological design that we are going to do. So basically, some formulation that just to let you know that this comes from somewhere, from numbers, and what we get at the end is that we can reach the same solution as the traditional methodologies, but without fitting parameters. That's it. So this is has more physical meaning than the other methodologies. And this is an example. If we impose here a pulling force, we fix 4 points here. At the end, we have a chair. So this is very simple, but it is what you expect. Okay. So the model can create a high core and then parts with a very low stiffness that at the end is you can remove. So that is why you create these kind of shapes. And this is just to show you that with the methodologies that we have now, that has some limitations. You can only apply one type of boundary condition, only linear elastic. You have 2 fitting parameters. You have the same solution with the more physically oriented formulation that we have done without fitting parameters. And here we are playing around with John modulus, and here we are playing around with penalization that is not directly related with John modulus. It is somehow, but not directly inside the formulation. So that one has more physical meaning, and that's why you have less parameters. And that was for linear elastic, but as you know, a material can be orthotropic. We can have different properties in the different directions. And we can say, okay, we are playing around with the strain energy. We are optimizing this energy through the mechanical parameters. Instead of having one, instead of having something homogeneous, we are going to have different in the different directions. If we do the same, we can optimize the different mechanical properties in the different direction. And this is the only published method that can do it. Can play around with orthotropy. So there is a method that if you play around and rethink the physics behind, you have a methodology without any fitting parameter that can go beyond to impose different boundary conditions, can be applied to different material configuration, and is at the end more generically and more physical sense, because you are optimizing the mechanical variables. So once you have this, what we have done is that we have a software that says, okay, from this methodology, you have a field of mechanical properties. So this software and a shape. This software take this and introduce a metamaterial. And with the metamaterial, which are those rebars, you can reproduce this variation of mechanical properties. And if we try this in a calculation software, we have the same capabilities that we have imposed at the beginning. So all the pipeline is working properly. We have also in the group patented a metamaterial design that can be auxetic. It means with a negative Poisson ratio and not auxetic. We have validated with different calculations, in lag strain, or we are trying dynamic. And we are also investigating in the role of the defects into those structures, because when you are 3D printed, this is not completely clean. You have some defects that at the end change your mechanical properties. So we are also researching this. Another quite new research line is the optimization of profiles. This is a wind profile that we start with a circle into the flux of air, and we start changing this with an evolutionary algorithm, and this evolution tends to have the shape of a wing. And this is only a methodology of interpolation, that the colors are where the point is taking the information. So when it's red, it's taking the information from one point, and well, the different colors are illuminating different things. What I mean is that we are playing around this field and expanding into different branches to see application and to see how can go beyond. And very quickly, I will go to another research line that we have here in Ausinos, which is the engineering. So, and it goes from the cellular behavior, we have something more to do with statistics and game theory, to the growing of vessels into a tumor, which is called angiogenesis, and information communication through the brain, which is something that we are starting now. So the behavior of the cells, each individual has some parameters to govern its behavior, and at each point, depending on the information that you have, make a decision, going here or there, or staying quiet. And also there are rules that are dying and so on. So we can reproduce the necrotic core, which is, those are cancerous cells. We can reproduce the flocking, which is where when they associate and just move in a group. And this is just the tracking through the resources. All of them go to the place where you have oxygen. So with those things, our aim is to reproduce at some point, to reproduce what is happening in a cancer, in a tumor. Okay, and with this we can study how to make the surgery better, the treatment, so on. And this is uncertainty. This is a very, very simple model that of vessel growing, and it runs very fast because it's very simple. So the vessel just take a decision and go according to the gradient of oxygen in this case. Well, this is the cells produce something called VEGF when there is a lack of oxygen, and the vessels are just following this marker. And with this, we can reproduce many things that agrees with experimental data that we have. So in a very simple way, we can reproduce this. And this is very important for the tumor evolution. And also when you have the metastases, that the cancer cells migrate to different places, this inserts a very important role. And we are also researching on biomechanics. because at the end it's a mechanical thing that can be stretched, that can deform, and it changes the way everything is, everything behaves. And this is what I told you of the brain. Just this is an ongoing work, but just pretty pictures. So many thanks. This is the two of our research line, roughly, which are the advanced structural calculation, and the materials, the engineering, and then Alberto is going to show you all the machine learning stuff that we are doing here in the group. Sí, estamos. Eran muchos. Nunca había, entonces se están organizando.
Vale, ¿has mirado si se ven los vídeos? ¿O enchufo el mío?
Lo que quieras, espérate.
Porque esto es HDMI.
Eso es USB.
Ah.
Yeah. Yeah, please. Well, the first thing that you need to do is to observe the physical problem, experimentally what is happening, and after this, you need to start putting numbers into this. So at the end, you came out with very simple models because you know that the explanation should be simple for the cells moving or whatever. So you need to start from the step by step, just modeling with very simple equations, very simple behaviors, and from this you can start scaling. But you need to do it this way because otherwise it's very difficult. Okay. Any other question? No?
Yeah. When you want to build a visualization given that you choose an hypothesis,
Yes.
you try to minimize the loss with this hypothesis.
Yeah.
Of the first part of your presentation, it was hypothesis considering the energy.
Yeah.
Why especially using the energy to find a solution? Is there any explanation and benefits?
Because the energy at the end is what the nature is doing. So the nature always goes following the minimum energy, and this is followed through the strength. For example, if there is something in the bone called the